Welcome to Introduction to Composites. Today is the third day of the ongoing week, and in the last 2 days we have been discussing how polymer matrix materials are susceptible to change in temperature, and in that context we have explained the behavior of these types of materials as temperature increases. And what we have seen is that three important things. So, we will write down. So, first, for thermosets, not much changes before the glass transition temperature, right. So, but after the glass transition temperature, significant change in material property, and that includes density. So, if T is more than Tg, then significant change in material property and material breaks down rapidly after Tg is crossed. What this means is that the operating temperature range of thermosets should never exceed the glass transition temperature of the material. So, the maximum operating temperature should always be less than Tg for thermoset materials. This is a direct consequence of our discussion which we had yesterday. So, this is for thermosets. So, if we want to use thermosets, we have to know the glass transition temperature and we have to be sure that we remain below it. If we exceed it, then the whole structure may get destroyed very rapidly. So, we have to be 100% certain that we do not exceed the glass transition temperature. Second, we are talking about amorphous thermoplastics. Okay. So, in case of amorphous thermoplastics, if T is more than Tg, what do we see? Significant drop in material properties. If you see on the log scale, E goes down, it may go down by as high as a factor of 1000, okay. And then once glass temperature is exceeded, because all the connections between the polymer chains, interconnect between polymer chains is broken. So, these chains start flowing with respect to each other. So, the material starts flowing. So, there is no, it is not that we have to wait for a melting temperature for the material to start flowing. And as a consequence of that, we can say that the maximum operating temperature of these materials, the maximum operating temperature should never exceed Tg. We do not have to worry about the melting point in this case also, because the thing starts melting just above glass transition temperature, because all the interconnects are broken. So, this is for amorphous plastics. And the third thing is semicrystalline. thermoplastics. Semicrystalline thermoplastics. So, what happens in this case? If T is less than Tg, not much change, not much change. The material expands a little bit, it becomes soft a little bit, but not a whole lot of changes are happening in the system. Okay. The second case is if the temperature is more than the glass transition temperature, but it is less than the melting point, what happens? Some changes in material properties, okay, some changes. So, we saw it, some changes in material properties, but still the overall modulus is somewhat maintained. It goes down appreciably, but does not go down by a factor of 1000, and the material still retains its solidity, it still has a stiffness, its density is still not that high, that low, it still retains its density to a certain extent. So, some changes in material properties, and we can still use the material. We can still use the material, but if temperature exceeds Tm, then what happens? Material starts flowing, it melts, and because of this it becomes unusable. So, if we have to use the semicrystalline thermoplastic, we have to make sure that maximum operating temperature of the material should be less than the melting point, should be less than the melting point. So, this is an important thing to understand. Thermosets, we should never exceed the glass transition temperature. Amorphous thermoplastics, we should never exceed the glass transition temperature. Semicrystalline thermoplastics, if we are smart and if we design our structure correctly, we may be able to exceed glass transition temperature, but we should never exceed the melting point. So, the next thing I would like to do is we should get some appreciation of what are the values of these glass transition temperatures and melting points for different materials. Okay. So, we will just write down a table. So, we have polymer, different types of polymers, their Tg in degrees centigrade and their melting point. So, first we will write it for thermosets. So, thermoset materials. Okay. So, we have epoxy. So, what is the glass transition temperature? Depends what type of epoxy we are working with. It can vary between 100 and 250 degrees centigrade. Okay. And melting point for a thermoset does not have a melting point, it just breaks down after glass transition. So, it is irrelevant. Another very popular thermoset. So, these are the two most popular thermosets, polyester and epoxy. Polyester is much cheaper than epoxy, but its material properties, Young's modulus strength, are inferior to that of epoxy. So, polyester glass transition can be anywhere between 75 and 150 degrees centigrade. So, that is why if you want to use these materials at even some higher temperatures, people go for epoxies because they can take a lot of temperature. They can go up to 250 degrees, and once again its melting point doesn't exist. So the next guy is thermoplastics, and we will give you some examples. Okay. So the first one is polystyrene. So this is 100 degrees centigrade, and we are talking about the amorphous version of it. But then this is important, HDPE, high density polyethylene, and if you use a semicrystalline version of it, high density polyethylene, its glass transition is actually pretty low, minus 80 degrees. Okay. But if we are using its semicrystalline version, then we don't have to worry too much about the glass transition. What we should be really worried about is its melting point. So it melts at 137 degrees centigrade. Okay. Let's look at some other interesting numbers. Polycarbonate. So this is an amorphous guy, and it has a glass transition at 150 degrees. Nylon, this is very interesting. Again, nylon glass transition is pretty low, 50 degrees centigrade. So even during summers you can get close to 50 degrees centigrade, but its melting point is 255 to 265 degrees, pretty high. Some others, PEEK. What is PEEK? Polyether ether ketone. Polyether, it's a very good material, thermoplastic material for aerospace applications. Why? Because its melting point, glass transition itself is reasonably okay, 143, but its melting point is pretty high, 334, and for this reason it is also costly. The other one is PPS, polyphenylene sulfide. So this is 85 and this is 285. So this gives you an idea as to which temperatures are important, for what type of material. You cannot blindly or without thinking say, oh, glass transition temperature is the one we have to worry about for all materials. Okay. For instance, nylon or high density polyethylene, its glass transition occurs at minus 80 degree and something like that, but you can safely use it at least till 60, 70, 80 degrees centigrade, because its melt point is 137 degrees. For the same reason, this PEEK, you can use it maybe even up to 200 degrees centigrade, 200, 250, because its melt point is pretty high, 334 C. So you have to look at the material, and first you have to figure out whether it's thermoset or thermoplastic, and then if it is a thermoplastic, you have to again question and figure out whether it is having an amorphous structure or whether it has a semicrystalline structure. So this is important to understand. The last thing, very quickly in a couple of minutes, I like to give you some idea. So you will wonder, I had earlier explained that you can have the same material, nylon, an amorphous version and semicrystalline version. So what is it done to make semicrystalline version of some of these thermoplastics? And there are two, broadly speaking, methods which are used to produce semicrystalline versions of thermoplastics. The first one is the method of evaporation. Okay. So what do? What they do is they somehow, using some organic solvents, they dissolve the material in some solution phase and then they boil it. These organic solvents boil very easily at very less temperatures, so somehow heat it and remove this material, and when this solvent and when the molecule, these polymer chains somehow align themselves in a semicrystalline fashion, and you get a good semicrystalline thermoplastic. So that is the method of evaporation. So evaporation is one method, the other one is known as precipitation. So there are precipitation reactions which you may have learnt about in your chemistry classes when you were getting into engineering or even in high school, at high school level. So we make these types of, we inject crystallinity in polymers using either the method of evaporation or the method of precipitation. So these are the two methods, and this concludes our discussion on the overview of polymers. Now what we will start doing is we will start looking at specific polymers. We will start looking at specific polymers and we will understand their properties, little bit about their chemistry, not a whole lot, but little bit so that we have some understanding. And so we will look at thermosets, we will look at thermoplastics, we will look at ceramic based materials, we will look at metal based matrix materials, and that will give us an overview of different types of materials which are used for matrices. So we will start our discussion with thermoset materials, and thermoset polymers. And the first material we will look at is polyester. Amongst all the matrix materials which are used to produce composites, this is the least expensive. It is the least expensive and perhaps most popular. Okay. There are other materials also, thermoset materials, which are used in good amounts: vinyl esters, polyamides, phenolics and epoxies. But polyester is the most popular, but maybe the second number is epoxy, that is the second most popular. Then we have vinyl esters, phenolics and polyamides. These are the different materials, but this is the most popular one, and maybe this is number 2. Okay. How is polyester as a matrix material made? Okay. How is it? So first thing we will learn is how is it made. Okay. So it has two terms. There is a poly term and then there is an ester term. Okay. So the way it is done is that you have a resin. So this is about production. Okay. This is about production. So what is this resin? It has, unsaturated polyester. It has unsaturated polyester. So this is the resin, and this you mix with a curing agent. You mix with curing agent. So resin has what? It has long chains of molecules, but all the molecules are not well connected. Okay. There are a lot of unsaturated bonds, and then this curing agent is added, and when you add these, somehow reaction is created, and then you have the cross linking of all the chains. Okay. So curing agent is added so that you develop cross linking of the chains. So this curing agent is typically styrene. Okay. So when you add these two, then you have a chain, and in presence of curing agent you will start developing these cross linking. So the everything becomes solidified. Now, if you add these two guys just by themselves, the reaction will not happen. So, for this there is also something which is known as a trigger or initiation agent. So, it acts like a trigger. Okay. So, for instance, I will give you an example. You take hydrogen and oxygen, you mix them, they will not react, but then you have to trigger it by providing a spark or something. So, similarly, the this thing that you add a trigger, and this trigger is typically known as examples of it could be benzyl peroxide. Okay. So, this is the trigger, excuse me. So, maybe this is probably the not correct term. I will call this monomer, which is the styrene. So, this trigger, when you add, so when you add all these three things up, then you get this cross linking in the resin and you get polyester. And the thing about is that if you process them in the right proportions, you add resin and monomer in the right proportion, you do not get any byproducts. The whole of this monomer, it gets absorbed into the resin and you get one final product. And then you have the final product and everything is well cross linked, and these cross linked bonds are covalent bonds. So, they are very strong. So, by regular at small temperatures they do not break easily. Only once you cross the glass transition temperature these guys break and the whole thing collapses. Now, another thing is that in the production process there is a lot of heat generated. Actually, it becomes very hot. Okay. So, it is an exothermic reaction. It is an exothermic reaction. And so, what that means is that you are mixing these two things up, and suppose you are also having fibers in process in the composite. So, in when you want to make a real composite, what do? You put resin and monomer, you mix them, that is the raw material, but you want to start the reaction. So, suppose you want to make a composite, you take resin plus monomer or styrene, mixture of it, mix it with fibers or the fabric, and then you somehow also add to it trigger, and as a consequence of it things start heating up, things start getting cured and things start becoming solid. But this solidification happens at an elevated temperature, not at room temperature, because there is a lot of heat which is generated. And so, the solid becomes formed at the higher temperature and then it cools and it comes to room temperature, and when it comes to room temperature internal thermal stresses get developed, and if your engineering or the design of the composite plate is not correct, you may not get a flat or the desired shape, it may be bent or warped from the shape which you want. So, this is an important thing to understand. The other thing is that in this process you have shrinkage. Okay. So, you have let us say 10 liters of the overall material resin plus monomer, but when it becomes solid the overall volume shrinks, it shrinks. So, this shrinkage also has to be understood and accounted for while the thing is being used, polyester as a resin. So, this is some basic idea about polyester. We will continue this discussion tomorrow also, and then we will discuss polyesters, we will discuss epoxies, we will discuss other matrix materials also, and that's how we plan to proceed. So that closes our discussion for today, and tomorrow we'll continue our discussion. Thank you.